Work about 1 mile from here. Over, if you go to LaPorte Avenue and go west, there's a part of CSU has a foothills campus, and I sit out there. I actually work for what's called the National Oceanic and Atmospheric Administration, or NOAA, and we do weather. And so that's what I'm going to talk to you about today. Specifically, we work with satellites, and so this is a photo of a satellite, and this is the Earth, one of the images that the satellite was able to capture. So I'm going to start off by showing a video, and I'll explain after the video why I'm showing the video. So I have it loaded here, and it does have some sound, so I'm going to turn this on.
T-minus 30 seconds and counting.
28.
ECS reduced for launch. Roger.
25.
Status check.
Go Atlas. Go Centaur.
Go goes R.
15 seconds and counting. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of NOAA's GOES-R, America's most advanced weather eye in the sky, elevating environmental intelligence to new heights and saving lives.
Neo's gone to close-up control. Engine response looks good. Now flying the zero angle attack phase of flight. Body rates look good. Booster has throttled down as scheduled. Response looks good. Roll program is complete. Body rates controlling down the middle.
Listening to the
refer to this as a launch vehicle. What we're doing is we're using the rocket in order to send a satellite up into space. Now you can't see the satellite, but it's actually housed in the very tip of the rocket up here. They put it at the top and they put the cone on, and then everything else below here is just a piece of the rocket that mostly contains fuel in order to fuel the rocket up into space and put our satellite where we need it to go. One more quick video. This one doesn't actually have any sound, but this shows what the satellite actually looks like, because it's a little bit hard to picture if you don't really understand. So that's the size of an average human. This is the size of the satellite. So it's something like the size of maybe a large van or a small bus, something like that. Has lots of different instruments on it. I won't talk to you about every individual instrument. It also has these solar panels. And so what it does is it uses the energy from the sun in order to charge its batteries. And that's how it obtains power when it's up in space. And it's able to, it has a little thruster there, so they're able to move the satellite around once it's in orbit. And the instruments, I think it'll spin around in a second here. These are the instruments, and this one here is called the Advanced Baseline Imager. That's the one I'm going to be talking to you about today. It's the one that takes the pictures. You can think of it as being a camera looking at the Earth and taking pictures every so often. And one other thing which I'll show on the next PowerPoint slide is we put the satellite at what's called geostationary orbit, which is way far away from the Earth. It's about 22,000 miles away from the Earth. And there's a reason for that, and I'll explain in just a second what that is. All right, so let's go back to here. You may not have talked about weather satellites yet in class, but there's two major types of orbits that we do, and those are called polar orbitings and geostationary. And the polar orbiting is this one here, and the big difference is the polar orbiting are really close to the Earth, and polar means, in the north or the south poles. And so those orbit really close to the Earth, and they go really fast around the Earth because they're really close. So since they're closer to the Earth, the pictures that they take are higher resolution. They can see things smaller on the Earth's surface. Geostationary, which is the one that we just saw launch, is 22,000 miles away. The reason it's that distance is because the rate that the satellite orbits the Earth is the same rate that the Earth spins. And so if I'm the satellite and I'm looking at the Earth over there, and the Earth is spinning and rotating, and I'm orbiting around, I'm always looking at the same point on the Earth's surface. And the advantage of that is you can take a picture and then wait another couple minutes and take another picture, and wait a couple minutes and take another picture, and you're seeing the clouds moving on the Earth's surface. And that's the reason we do that. It's a big advantage to be able to see clouds move. And I'm going to show you some movies in just a minute of lots of examples of what I mean by the clouds moving. There's all sorts of satellites up there. These are GPS satellites in order to provide better geolocation on the Earth. There's communication satellites. There's all sorts of things going on. But the ones I'm going to talk about today are these weather satellites. So this is the type of image that the type of pictures in the movie that we're able to take from this GOES-R satellite that I was talking about. Now it looks like it's staying in the same place because it has the same image at all times, and the only thing that's changing is, in fact, let me just ask this question. What are we seeing here? Does anybody know why we have this black area moving through? Yeah.
Because of the sun, because it's not shown on the Earth because the Earth is changing.
Exactly right. Yep, that's right. So if we're looking at visible wavelengths, in other words, the wavelengths that our eyes can see, we can only see the Earth when the sun is reflecting off of the clouds and coming back to the satellite. But at nighttime, there is no sun. The sun's on the backside of the Earth, and so it's dark. And that's the reason we see the sunset line passing through here. You can see this is the entire area that our satellite can see. The map is not on here, but here's North America, here's South America, Central America. So we can see hurricanes coming across the Atlantic. We can see other things in the Pacific, and of course we can see storms and snowstorms and things like that over the U.S.
When was this taken?
This was, I believe, about 3 months after the launch of the satellite. I showed you the video of the launch. It takes a while for the satellite to get up there. They have to turn on the instruments and do some testing. And I believe this was January of 2017. So what is that, a year and a half ago? Something like that. Okay, this is the reason that we have geostationary satellites, because we're able to take really cool movies like this. Anybody know what this is? Yeah. It's a hurricane, yeah. Does anybody, well, it says it up here, doesn't it? It kind of gave that away. This is Hurricane Harvey. You may remember this from about a year ago, a little more than a year ago. This is the coastline of Texas. This is the Gulf of Mexico. And this hurricane moved in and caused serious damage around Corpus Christi, Texas. Houston is up in this area. Corpus Christi's down here. And the storm ended up stalling and dumping about 50 inches of rain in parts of Texas, and it caused some major problems. It stopped looping, so I'm going to restart it. But what the satellite is able to do is take a picture. In this case, every 30 seconds, it takes an image, and then it takes another image, and we're able to see the spin. This is the eye of the hurricane, and we can see the clouds spinning in the middle of the eye, which is something that our older satellites weren't able to do. This is sort of a newer, more advanced instrument that we have on this particular satellite. So weather forecasters use this information. Say that you're a weather forecaster and you're trying to give the forecast for somebody living right here on the coast of Texas. They can look at this imagery and say, here comes the hurricane. You people living on the beach here, you need to get away, you need to evacuate. And that's exactly what they did in this case. They were able to save lives by requiring that the people living along the coast here move inland or go somewhere far away. Because the hurricane with really strong winds and also water can cause some serious damage right along the coastline.
Is this picture, this video from your geospatial satellite or from the polar satellite?
So this is a video from the geostationary satellite. This was actually from that same satellite that launched on the rocket that I showed at the beginning. The way you can tell that it's the geostationary is the fact that we have a movie. We have moving clouds. The polar orbiting will take a single snapshot and then it's gone. And then you have to wait something like an hour for it to come back around the Earth and take another picture. In this case, since we're able to get an image every 30 seconds, that means that it must be a geostationary satellite. I have more hurricane examples. This one is another one from last year called Hurricane Irma. This was when it was out over the Atlantic Ocean, and we could get really high resolution pictures and looking in the middle of the eye and see down into it. These are higher clouds on the outside. In this case, if you happen to be in a boat in the middle of, you wouldn't want to, but if you happen to be a boat in the middle of the eye, it's actually relatively calm winds there. But you go just outside of the eye, and that's where you have really strong winds. It can be like 100, 150 miles per hour winds, something like that. And so any boats that are in the area of hurricanes, they have them go away because they produce huge waves and very, very bad for ships and boats. Here is another picture. Now this one has color, right? And we were looking before at black and white imagery. And the difference is the satellite can not only detect radiation from the sun, like our eyes can see, but it also can detect what's called infrared radiation. And that's at a different wavelength, and it means that we can see the clouds at night as well as during the day. The colors here represent how high the clouds are up into the atmosphere. As you get into the reds and the blacks, that means higher and higher clouds. And in general, in meteorology, the higher and the deeper the cloud is, then the stronger the storm is. So thunderstorms will have high cold clouds, hurricanes will have high cold clouds. Other clouds, like up in this area, they're lower and they're warmer in this case, and they aren't that big of a deal. They can produce rain, but if you're gonna have thunder and lightning and the type of weather you get around hurricanes, those are gonna be big, deep cold clouds. This was Hurricane Maria, yet another one from last year. This is Puerto Rico, and you may remember this in the news. Hurricane Maria came in and came on shore in Puerto Rico and caused some significant damage, knocked out a bunch of their power and their infrastructure, and they're still actually recovering from that now. One more, this is actually a different satellite from the one we were showing before. This is a satellite that's over the Western Pacific Ocean that the Japanese launched, the Japanese Meteorological Agency. And it's called Himawari. It has a similar instrument, and they have big storms in the Pacific over there. They call them typhoons, but a typhoon and a hurricane are really the exact same thing. The only difference is where they're located on the Earth. When they're in the Atlantic Ocean or the East Pacific Ocean, we call them hurricanes. When they're in the West Pacific, which is around Japan, we call them typhoons. When they're in the Southern Hemisphere, around Australia, we call those cyclones. You'll hear all these different terms, but it's really the same thing. It's just a different terminology depending on where you are. Okay, here's another one in the Southern Hemisphere. This is a good quiz to see who's observant. Does anybody notice anything different with regard to the way that this one is spinning compared to the one that we saw before? Yeah.
There's blue lines.
The blue lines are different. That's right. These are.
No, I mean the blue like square lines.
These here, that is different. We did not put, these are called latitude longitude lines. We did not have those on the previous. But in terms of the way the hurricane is spinning, yeah.
It's sort of going almost like just one circle around something, or like this sort of. I sort of saw both of these. There's just one big circle and also like a spiral into it.
Yeah. Yeah, it does look a little bit different in terms of the spiraling. This one is a little bit.
One big, like the hurricane itself is like only one circle.
Right.
Like around the area.
Okay, I see.
Just like itself.
Yeah, I see what you're saying. That's very true, and it's a good observation. What about the direction that the storm itself is spinning? Yeah.
It looks more clockwise, or I don't know if that's counterclockwise. I don't know, but the other ones kind of look like they're spinning the other way.
Exactly. That's exactly what I was looking for. The direction of the spin is different from this storm compared to the last ones that we were looking at. And the reason is, in the northern hemisphere, these hurricanes will spin in this direction. If you think about a clock, this is actually in the counterclockwise direction. There you go. Yeah. If you look at the direction that the second hand is moving. If it moves in this direction, like the clock, that's called clockwise. And if it moves in the other direction, that's called counterclockwise. So in the northern hemisphere, which is the Atlantic Ocean, the storms we were looking at, those move in the spin in the counterclockwise. In the southern hemisphere, they spin in the opposite direction, in the clockwise direction. This was Hurricane Winston. This is the southern hemisphere. This is the island of Fiji in the South Pacific. We'd have to pull up a globe or a map to show you exactly where this is located. The reason that they spin different is something called the Coriolis effect. And it's not anything I want to bother explaining right now, but it's something that if you take meteorology classes later on, even in high school or in college, you'll learn a lot about something called the Coriolis effect.
And as a little teaser, we're going to be learning about that in our next unit.
Oh, good. I wasn't sure if you guys covered that or
We will
not.
touch on it just a little bit.
Cool. Okay, so I'm going to switch gears a little bit and talk a little bit more about that rocket launch. So I was actually able to go down and watch the rocket launch in person, which was a really cool experience. And we launched these satellites from a place called Cape Canaveral, Florida. This is just a Google Maps. This is Orlando. Disney World is down here somewhere. The Atlantic Ocean. Here's Cape Canaveral. And they launched these satellites from right in this area in Kennedy Space Center. And so I took some pictures whenever we went down there. We actually had a cake, Gozar cake, which I thought was cool. Gozar is the name of the satellite. And that's the reason I keep saying GOES-R. GOES stands for Geostationary Operational Environmental Satellite. And then R, it refers to sort of the order. We do R and then S and then T and then U. And once they reach orbit, we change from the letters to the numbers. So once GOES-R, this satellite reached geostationary orbit, we started calling it GOES-16. So they go from letters to numbers once they reach orbit. These are some of the photos I snapped while I was down there. This is a NASA facility. NASA helps us launch the satellites. I don't work for NASA, I work for NOAA. They're both federal agencies. NASA does more things with space, and NOAA does more things with Earth observing. But this is a giant building down there called the Vehicle Assembly Building that's been there since the 1960s. And this is where NASA builds big rockets. The rocket that I showed you wasn't built in this particular building, but some of the different ones are built here. And to give you an idea of how big this building is, that flag on the side of the building is larger than a soccer field. And so this was actually taken from a pretty far distance away, and as you get closer and closer, you can see how gigantic the building is. This is the inside of that building, and it was hard to get a good picture. These are 3 different photos looking sort of up. And the reason it has to be big is because these rockets are really big when they build them. And so they bring them in, and then they have these scaffolding all around, so the workers can climb up on the scaffolding and put the pieces together on the rocket. And then they wheel them out to the launch pad from there. This was what, I got to go close to the rocket the day before the launch. And so this is what it looked like up close. This is what the launch pad looks like. Now, once the rocket starts to launch, nobody's allowed to be anywhere near there because it's very dangerous. You're producing a lot of heat, and we had to be far away. This was me looking and pretty excited about being able to get that close to the rocket on the day before. Here's another map showing where I was able to watch the launch from. This is the launch pad is located here, close to the beach. I was about 5.4 miles away at a place called Banana Creek, looking in that direction. So keep that in mind when I show you the next. So this was the photo that I took from the launch location. There was a lake between me and the launch. You can barely see it. That's about 5 miles away. So the coolest part of this whole experience in watching this launch is, so you may have learned already that sound travels slower than light. And that's the reason that in a thunderstorm, you see lightning and then you have to wait some amount of time before you hear the thunder. With a rocket launch, we see the rocket launch, but then it takes longer for the sound from that to reach. So we actually saw the rocket go up, and since we're 5 miles away, if you do the math, it takes about 30 seconds for the sound to arrive. So we watched the rocket go up, we didn't hear anything at all. It was complete silence until about 30 seconds later, we started to see ripples in the lake before we heard anything. And what that was the sound waves, as they came closer, were causing ripples in the lake. And then we heard the sound, and at that time, the rocket was already up here somewhere. So I thought that was a really cool thing. I should have gotten a video of that, but it was pretty dark. It was right at dusk, and I wasn't able to do that. Okay. So I want to say a few words about my career as a meteorologist. Nicole asked me to do this, and it's something for you guys to kind of get an idea of maybe something that you might want to do in the physical sciences, and meteorology is something that's sort of a specific physical science. So, excuse me, I grew up in Georgia, and in Georgia it doesn't snow nearly as much as it does here in Colorado. You guys are used to the snow, you're lucky. I love snow. But so anytime it actually snowed in Georgia, it was a big deal. Back in 1993, I was in high school, long before you guys were born, and we had a big snowstorm on the East Coast called the Storm of the Century, and it dumped 16 inches of snow at my house, which, you know, you guys, 16 inches is probably not a big deal, but in Georgia, it was a huge thing. It was super exciting. We had no power, no water for an entire week, no school for a week, and so we were out playing in the snow the whole time, of course. This photo was taken not in Georgia, but nearby in North Carolina, and this was probably about the same amount that we got. Big deal, caused major problems, but as a high school student, I thought it was super exciting. It was really that weather event that got me really interested in weather. And I didn't necessarily decide at that point that I wanted to be a meteorologist, but I decided that I was really interested in this. And so when I went to college, I wanted to take some classes and learn more about meteorology. So that storm made me very interested in weather, and so I went to the University of Georgia. It's a school about the same size as Colorado State, something like that. And I took some weather classes, and I really liked them. A lot of universities will offer various classes for anybody to take. You don't have to be a major in that. So if weather is something you're particularly interested in, you can take a class in college, and you may like it very much. And then if they offer that as a major, you can major in that. Now, at Georgia, they don't actually have meteorology as a major. It's not something that's at every single school. They don't have it at Georgia. They also don't have it at Colorado State as an undergraduate major. So I talked to one of my professors and I said, if I want to be a meteorologist, what should I do? They don't offer meteorology here. And he said, well, you could go to graduate school. And I don't know if you guys know what graduate school means, and that's basically the next level after you go to college. You can get another degree in graduate school. So he suggested that I should plan to go to graduate school and major in something different at Georgia, something that's supportive of meteorology. And what he suggested and what I ended up doing was majoring in math. Now, I don't know if you guys are fans of math, but it's a fact that math and science really go hand in hand. You can almost think of math as being a toolbox for scientists. Not all scientists use math heavily. Some of them do, some of them don't. In meteorology and atmospheric science, we do. We use math quite a bit, and it's important for things like weather forecasting, which I'll explain more of in a minute. So I got a major in math at the University of Georgia, and then I came out to Colorado State in Fort Collins way back in 1999 for graduate school, and I've been here ever since. So after getting the graduate degrees at CSU, I got a job at NOAA, a mile and a half away or something from here, very close by, and that's where I work now. This is a great career choice for me because I really love weather. I would consider myself a weather geek. I get excited when there's snow or rain or anything like that. And it's really good to find a career that you really enjoy doing, if at all possible. Okay, so math and meteorology. I just wanted to show, these are some equations that you guys have not covered yet. You're probably learning algebra and geometry and things like that at this point. This is later, a little bit later on, maybe getting into the calculus range. But it's this type of information that you'll learn in college if you want to be a math major and certainly a meteorology major. I know it's too hard to explain right now, but the way that weather prediction works is we take this set of equations and we're able to solve them, or at least approximate the solutions for these equations of what's going to happen in the future. So if we know right now what the temperature is, what the atmospheric pressure is, what the water vapor is at every location on the Earth, then we can use these equations to predict what that's going to be in 1 hour, what that's going to be in 2 hours, what that's going to be tomorrow, et cetera, et cetera. And we build what's called computer models in order to do this. And that's the way you go to your TV weather forecaster and he says, oh, looks like it's going to rain tomorrow. The high temperature is going to be 40 degrees. The way that they know that is actually because of math, because of equations like these and the weather models that they build. I'm not trying to scare you here. It's actually, it's a lot of fun once you get more into it. Okay, so a typical work day for me. I'd like to say that I'm going out with a thermometer and doing things out in the field and traveling all over. It's really not that fun. What I'm really doing in general is sitting in front of a computer. And I think a lot of times these days in any sort of science field, that's often the case. Not always. There's labs and there's different types of sciences where you're doing experiments and stuff. But for the most part, what I do is I'm sitting in front of a computer and I'm doing various things. Emails doesn't sound very, very exciting, but that's kind of communicating with the peers across the U.S. and across the world. Computer programming is important for weather. So if any of you are into computers, if you're going to do science, I definitely recommend taking computer programming classes when you can. I don't know if you guys offer them here at Polaris, but yeah, and when you get into college, think about that. Think about taking some computer science classes and learning how to program. I think going forward in today's world, computer programming is going to be really important, even more so than it is now. And then I look at a lot of satellite imagery. I've shown you some examples already, and I'm going to show you more in just a few minutes now. And also look at weather forecast models. I'm always worried, when is it going to snow here? I love snow, so I'm always looking at the forecast. And we thought maybe this weekend, this Sunday and Monday, we might see a little snow. Now it's probably going to be a little bit too warm. Not a very good probability. But that's my average day. Again, not all that exciting. There's a website here I'm going to show you at the end of the class, at the end of when I finish talking, that is a fun place to go to and check out yourself, so that you can play around with satellite images in real time. And what I mean by real time is it means it's happening right now. You can go on there and you can zoom into Colorado and you can see where the clouds are. And it's really a nice tool for learning about the weather and seeing what's going to happen with clouds. Okay, so I'm going to show some more examples and I'm going to ask some questions along the way if anybody various quizzes. So this is yet another image of the northwest part of the Earth. This is the coast of Washington and Oregon in the Pacific Ocean. What's that? The moon. I guess that was a pretty easy one, wasn't it? So sometimes, just depending on the timing, the satellite happens to catch the moon as it's orbiting around the Earth. And in this case we did. It's actually a really neat picture there. And it was so neat that we sent it to NBC News, and they showed it on TV. This is Al Roker. I don't know if you ever watched the Today Show on NBC in the mornings, but I took this picture of my television, I think, as he was showing our image there of the moon, which was pretty awesome. Okay, so I'm going to show you various other satellite loops. I think up until this point I was showing you mostly hurricanes. I want to talk a little bit about thunderstorms too. This is the state of Georgia. This is actually where I grew up. I grew up in this area and went to school over here. These are what thunderstorms look like from satellite. And you can, when we take an image every 1 minute, we can start to see these, it sort of looks like bubbles on the top of the cloud. And that's exactly what it is. These are clouds that are bubbling up into the top of the atmosphere. And we call this convection. It's sort of the same idea from a physics standpoint. If you get a pot of water and turn on the stove and it starts boiling, you start getting bubbles. It's the same idea here. It's basically heat from below that's pushing up and then coming up into an area that's more dense and coming back down, and it produces bubbles like this. And in general, the more bubbly the storm top is, then the stronger the storm is. So these storms were likely producing lots of thunder and lightning, and I believe that they also produced some large hail, which is pretty common around Fort Collins, not as common around Georgia. And then another thing we can do is combine one of these infrared wavelengths like I was talking about before with the visible, and now the colors represent how high the clouds are. And so the reds area are the higher clouds, they're the stronger part of the storm. The yellows and the greens are lower, they're the warmer part of the storm. And you can get an idea of what part is sort of the most dangerous. If you wanted to issue a severe thunderstorm warning, we would probably do it closer to where the red part of the storm is in this case.
So when we look at a weather map, like I have an app on my phone that I can look at the weather radar.
Yeah.
Whatever. Like, so is that what I'm looking at? Is the height of the clouds when it shows like the red and the yellow and the orange?
Yeah, that's a great question. The answer is no, and because what we're looking at here is a satellite view, so we're looking always from the top. A radar is something different. A radar sits on the Earth's surface and it spins around and scans. And what it does is it sends out a pulse of energy that bounces off raindrops within the cloud, and then it comes back and is recorded. And what the red that you're talking about from the radar indicates the intensity of the rain. So the more of the backscatter that you get, they color it. It's called reflectivity. The more reflectivity you get, then that means the more rain or the heavier rain. Or if there's hail, it's even really high like that. Okay. And so what we use, forecasters really use both radar and satellite together. Okay. The radar tells you what the rain is doing, and the satellite tells you what the clouds are doing from above. And both of these, radar can't see clouds, and the satellite can't see the rain. And so they're sort of seeing different sized things. Rain is bigger, cloud droplets are smaller. Yeah?
So do you have any, like, that type of stuff on the recent tsunami or something like that?
Not the tsunami. So a tsunami is something that happens in the ocean. And so we actually, one thing I try to do is see if we can sort of see a tsunami from satellite. And up until this point, we haven't been able to. It's mostly happening underneath the ocean surface, a little bit on the top of the ocean surface. But no, we can't actually see a tsunami from the satellite, unfortunately. Yeah.
It's kind of like Nichols' app. I think on my dash GPS instruct, he also has the weather thing. And I noticed also, like at first I also thought it was like the clouds covered, like saying, because it said where it was. I thought that was like the clouds, but
it may be.
it also said like on like a little scale, like how intense it would be, like really intense.
Right, yeah, so I think some of the apps will show radar, like Nicole was talking about, but also some may show satellite too, and that can be useful for deciding, I mean, if you want to have a picnic outside and you want to see when the clouds go away, then you may look at the satellite and see when the clouds move, something like that. And again, I'll show you some examples of that website in a few minutes here that allow you to go in and look at the satellite. Here's another example of a thunderstorm. This is the Texas Panhandle. Remember I said bubbly storms are strong. That's the case here too. This is called a supercell thunderstorm. Supercell means that the updraft or the rising air within the storm is rotating like this. And it's these types of storms that often produce tornadoes. Not always. This storm did not actually produce a tornado, but it did produce large hail in the area around Amarillo, Texas. Yeah?
Can you see tornadoes from space? Like in
Great question. And the answer is no. And there's two reasons why. Number one, tornadoes are actually quite small. They're maybe at the most about a mile wide, usually much smaller than that, usually say a quarter mile wide or even just a couple hundred meters wide. Satellites can't see with that resolution. We can't see things that are small. These clouds are gigantic compared to the side. Like a tornado, if this thing is producing a tornado, it's somewhere under the cloud and it's small. And so I think it would be really cool to see a tornado. It is possible in certain conditions if it's a really, really big tornado. But the second problem that I mentioned is that almost always tornadoes are occurring beneath a cloud. And therefore the cloud is shielding us from satellite. So in this case, if this was producing a tornado, it would be somewhere underneath the cloud, and we're looking at it from above, so we can't really see them.
Not you, but has anybody ever like seen a tornado? Like you say, like sometimes we can see them like if the conditions are ideal, like to see one.
Mm-hmm.
So does that mean that you have seen them before?
You mean actually with my own eyes and seen it?
Not you. Like
not me personally. Oh yeah, people see tornadoes all the time. I've actually seen a couple. When I was a student 15 years ago or something, I would occasionally drive out to eastern Colorado trying to see a tornado.
I mean, on the satellite.
Oh, you're talking about from the satellite.
Yeah. Has
Okay.
anybody ever seen it on a satellite?
I don't think so. And I think it would be really cool if we were able to. Like I say, the only way it would be possible is if the winds were blowing the cloud off to the side and we were able to sort of get a view underneath the storm, and also if the tornado was really big. Because remember, we can only see small, relatively big things, big clouds from the satellite, not small things like tornadoes. Okay, this is I finally have a Colorado example. These are really strong thunderstorms that occurred in Colorado in May of last year. To get your bearings, Fort Collins is up in this area, something like this. Denver is actually right underneath this storm here. And this storm, the really bubbly one right there, produced large hail and damaged Colorado Mills Mall, which is in Lakewood. And it was closed. Colorado Mills Mall was closed last year from May up until December because of the damage produced by this storm right here. I think what happened was the hail was big. It busted the skylights and water, the rain ended up getting in and causing some flooding within the mall. Okay. Who can tell me what we're seeing here? Yeah.
United States.
United States is absolutely correct. Specifically, what else are we seeing that makes this a little bit different? Yeah, go ahead.
The moon.
Are we seeing the moon, or are we seeing
the shadow?
The shadow of the moon? That's exactly right. So raise your hand if you remember the solar eclipse from last summer. It was a pretty big deal around here, so most of you probably do remember that. This is what the solar eclipse looked like from the satellite. And yeah, you're exact. Does everybody see the black shadow passing through? That is the moon shadow. That's what the eclipse looked like from satellite. Now, it wasn't as cool probably as seeing it from the Earth's surface, especially if you were up in Wyoming where they got to the totality. If here in I didn't get to go to Wyoming, unfortunately. I watched it from here in Fort Collins, and we got to something like 96% coverage, which was really cool because it got a lot darker. But the videos and the pictures that I saw from Wyoming were awesome, and I regret not going up there.
So I have a question about this.
Yeah.
It looks like there's less. It looks like when the shadow comes through, those clouds that are moving northeast in the Nebraska area actually like stutter a little bit. Like they almost slow down when the shadow comes through. Do you think that there's less heat energy coming and they kind of stall, or am I just trying to find something that might not be there?
So it's hard to say on this particular whether that happens or not. I should have provided a different zoomed in view, because what you're suggesting does happen. Not in terms of causing the clouds to stutter, but let's look carefully over Arkansas. Let's wait till it starts over. Notice how we have lots of these these are cumulus clouds. See how there's a lot of them? And then after the shadow passes through, they're gone. And the reason is because these cumulus clouds, they are being driven or forced by the sun. The sun is hitting the surface and it causes this convection, it causes the clouds to form. When the moon's shadow passed over, it cut off the sun. It sort of cut off the driving mechanism and the clouds dissipated. And so depending on where you were, people were observing this. If they were watching the eclipse from Arkansas, they noticed there were clouds, and then suddenly the clouds are gone. And the reason is because we lost the solar heating, and then after the sun came back out, whoop, they pop back up again because the sun comes back in. There haven't been a lot of solar eclipses, so we don't really have a lot of data to study sort of the effect that eclipses have on the weather. It's a somewhat rare thing to get the total eclipse like we did last year. All right, what are we seeing here? Yeah.
Fires and smoke.
That is exactly right, fires and smoke. So this is another thing that the satellite is capable of seeing, not just clouds. What's that?
Isn't that Montana and Idaho?
It is, Montana, Idaho, northwestern Wyoming. This is the Yellowstone area here.
With Oregon or Washington?
Yep, I think that's the east side of Washington right there. Okay, so these red and yellow areas, they look like flames, don't they, from the fires? They're not actually flames. We can't see the flames themselves, but what we can see is the heat from the fires that they're releasing. And so we measure the heat, and then we color them yellow and red in order for them to show up. And therefore, if we're looking at this, say that you're a weather forecaster, and you're trying to tell the firefighters who are out there fighting these fires where are the hot spots, where do you need to avoid, or where do you need to warn the public. And what they would use this information to say, okay, they would draw a little line around the fire right there and say, here's the fire boundary, here's the way that it's moving. And they get that information from the satellite. And then at the same time, we can see the smoke and the clouds associated with that. And these are massive smoke plumes from these fires. There was a big fire year. Do you guys remember, I believe it was 2012, which was a number of years ago, some fires just to the west of here, and some big smoke plumes came over Fort Collins. They probably looked similar to this, except this one was up in Montana from the end of last summer. So satellites do more than just look at things like thunderstorms and hurricanes, but they also look at smoke and fire. Yeah. Volcanoes, absolutely, they can. And I don't remember if I have any examples with me, but if not, if we have time, I have one on the web that I can show you. They don't necessarily see the volcanoes themselves, but they see the eruptions from the volcanoes, which I think is what you meant. Yeah. All right, this is just another example of fires. This is up in Canada, pretty far to the north. I believe this is the Northwest Territory. It's either Alberta or Saskatchewan. I think maybe this is Alberta and this is Saskatchewan. Lots of big fires burning up in Canada. There's not as many people in general up there. And so a lot of times they'll just let these fires burn because they're out in open regions. And it's something that happens every single summer. Lightning strikes and things like that will start the fires, and they'll burn large areas of forest up there and generate a tremendous amount of smoke too. Okay, so we're going to switch parts of the country, or sorry, of the world. And this is a harder geography quiz. I'll give you a hint. This is not part of the U.S. or even part of the Americas. Does anybody recognize where we are here in the world? What's that?
Is it near Russia?
It's near Russia, but it's not actually Russia. Yeah.
I was gonna say Australia.
Australia. It's a good. You're in the general ballpark, but we're actually in the northern hemisphere. Yeah.
Eastern China or like Eastern Asia?
East Asia is exactly right. So this is actually Western China up here. This is India down here. And Bangladesh is kind of hard to see the lines, is right here. So this is a different part of the world altogether. This is a different satellite. This is the Japanese satellite that I was talking about earlier. The reason I showed this example is another thing that the satellite is able to see is pollution. And if you look carefully, the Himalaya mountains are right here, right along through the country of Nepal. Mount Everest is somewhere in here. What those mountains do is they serve as a barrier between very polluted areas in India to the south and very clean, pristine areas to the north. This area is also known as Tibet, or the Tibetan Plateau. You may have heard that term before. Very clear, clean skies, go south into India, significant pollution down there. This was a day where I think the pollution was even worse than normal, so it provides bad air quality, not really a great place to have to breathe the air down there. Here's another example from Western China. Let's see if anybody can watch this 1 or 2 times through and then see if anybody can tell me what it is we're seeing. Not the clouds, I'm not talking about the clouds in this case. Anybody make a guess on what we're seeing? Yeah.
A storm, maybe?
A what?
It's not a dust storm.
Dust storm, yeah, that's exactly right. And how do we know it's dust? Well, in this case, it's brown. That's a pretty good clue, right? And it just, you've probably seen pictures online and videos of things called haboobs. They're like these big walls of dust that move in, especially in desert areas. And that's what we're seeing here. These are some mountains in western China. The dust is coming from, I think, from a dry lake bed somewhere over here with strong winds. And it comes through, and then it actually goes down through these little mountain passes right there, spills down, and then through a mountain pass there, and here's just a big wall of dust moving through. So again, we use the satellites to look at more than meteorology, things like dust storms too. So I mentioned the rocket launch, and I showed you the video. That was in the end of 2016. In March of this year, we launched our second satellite with similar instrumentation called GOES-S. Remember I said R was the first one, S is the second one. And this was last summer, in June of last year. They put these satellites together down in Littleton, Colorado at Lockheed Martin. It's a company down there. And I had the opportunity to go down and put on this fancy suit and go take a look at the satellite. So this is actually what the satellite looks like. Not all the scaffolding, but this back here in the background. This is the satellite before they put it on the rocket and before they launched it into space. This is me. You may not be able to tell. But they make us wear these suits because they want to be really careful about little pieces of dust and dirt and things like that falling off of our clothes, and that can cause some damage to some of these really high-tech instruments. All right, I think that's the last picture I had. I want to show that website, and then I can take more questions if you guys have any. Okay, so the website, if you want to write this down for future reference, if you do a Google search for RAMMB slider, SLIDER, this will be the first thing that comes up. You click on that, and this is a so-called real-time animation from the satellite. And what I mean by real-time is the very last image that you're seeing there was probably in the last 30 minutes. It was really, really, really recent. And you get a very nice view of the entire Earth in that respect, yeah?
Which hurricane, is that a hurricane on the left of there? Which one is it?
You guys are becoming meteorology experts already. You found both hurricanes. Yeah, I was going to ask that, but you beat me to it. Yes, that's exactly right. We have 2 hurricanes right now.
Which ones are they?
I believe that this is Leslie out here in the middle of the Atlantic, and I'll have to go and look online and see what that one is. There's a Hurricane Center website we can go to and take a look, but I can't remember the name of it.
I also noticed a bit of like swirly cloud down at the bottom.
Down here, which way?
At the very bottom, like more to the right a little bit.
Down here?
Yeah.
Yep. So this is actually not a hurricane. This is something called a mid-latitude cyclone, and it's swirly. Yeah. It's a different type of storm though. It's but these are the exact. What you're doing right now is you're doing what meteorologists do with satellite imagery. They look at the imagery, they identify storms, they identify dangerous areas, and then they make their weather forecast based on that. So the cool thing about this website is you can zoom in. And you can take the mouse and you can pan around wherever you want to go. And you can use the roller button to zoom. So let's just zoom in over Colorado. And it takes a little bit of time to load because it's downloading the images, but let's give it a minute. And I'll stop it at the end and we can look and see what we can see. So here's Colorado. Fort Collins is probably right in this area, something like that. We don't have the counties on here, so it's hard to say exactly. But this white area here is the top of that cloud out the window that we can see. And it looks like it's starting to thin because the sun's trying to poke through. But this is what the clouds that we had this morning look like from space. Now, what this would tell you is if you drive to the east somewhere, out on the eastern plains, then you're going to get out of the clouds and it's clear out there because you can see the ground, you can see the brownness from the Pawnee grasslands. And you can use this slider bar right here to go back and forth and loop. I call this looping the clouds to get an idea of the direction that they're moving. You can see these clouds down here. These actually look like, to me, like they might be thunderstorms. which is maybe a little bit unusual this time of year. Most thunderstorms around here are occurring in the summertime, and now we're in the fall. But you do sometimes get fall thunderstorms. If you sort of extrapolate the direction these are moving, they're moving more into northwestern Colorado, so places like Grand Junction and Steamboat may see some rain from that, yeah.
Do you think it's gonna rain today?
That's a great question. I don't know. I think based on the weather models I looked at, there was a chance, but I think it's a less than a 50% chance. So the answer would be probably not, but it's a possibility. Does somebody else have a question? Oh, I saw a hand. Yeah.
Could you play the loop over again, but lower the speed?
Yep. So this right here is the speed bar, so we'll lower it down. So are you wondering about the beginning, why it's a different color?
It kind of looks like nighttime.
Yes, that's right. So what we're looking at here is a daytime image. At night, remember I said that it's dark. So the way this particular, I call this a product, the way the product works is it uses other information at nighttime so that we can see the clouds, we can still see the clouds. It uses infrared information. And it colors the clouds that are low clouds blue. And so you can tell the difference between the low clouds, which are blue, and the high clouds, which are white in this case. You can also see underneath the clouds the city lights. Now, this is a little bit tricky because we play some games with this particular product. You can't actually see the city lights with a satellite. So what we do is we use a different database of city lights, and we put that as sort of a background layer on this particular product. And the advantage of that is you can see where people live. We can find, so this is Denver, that is Boulder, Loveland, and Fort Collins is right there.
Can you zoom in?
You can zoom in one more level. This is as much as we can zoom right here. And if you look really carefully, you can identify even I-25 has little lights, and this is Cheyenne, this is Greeley right here, and you can find your city wherever you happen to be interested in. The reason this is useful is that you can find out exactly where the clouds are. As the sun comes up, we can see Fort Collins is right there. And then as the clouds come up, we were within the clouds. But Greeley, which is right here, is right on the edge of the clouds. So we can use this to say, oh, it was clear in Greeley this morning, but it was cloudy in Fort Collins. Let's do one more thing. Let's go over to the hurricane and zoom in. So this is that Hurricane Leslie that I was talking about. And one good thing about Leslie is it's out in the middle of the Atlantic Ocean. There's no land masses anywhere near there. So really, it's not a big deal. It's mostly a big deal if you happen to be on a ship trying to cross the Atlantic Ocean. You may want to avoid the hurricane. Let's look and see the name of that other hurricane. So there's a website from the National Hurricane Center, NHC. So they put out advisories and warnings and things on the various systems. There's Leslie. We have to click on East North Pacific to go to that one. That is Sergio, apparently. Sergio, click on Sergio, and then this will give you the forecast. Here's the location now, and they're saying that it's going to move to the west. And I'm going to look at the intensity, which is down here. They're saying it is 120 knots maximum sustained winds. That means a knot is approximately the same as a mile per hour. So about 120 mile per hour wind. That's really strong for a hurricane. It's not something you would want to experience in person, or certainly not on a ship either out in the middle of the ocean. It does. Oh yeah, you're right. So a knot technically means a nautical mile per hour, and mile per hour means a statute mile per hour. And a nautical mile and a statute mile are a little bit different. And so that's why 120 knots corresponds to 140 miles per hour. They're not exactly the same. All right. The last thing I'm going to show you, because I had a question about the volcano. There's another cool site called Loop of the Day that we put together. And this is an archive of lots of many loops. I'm not going to go through all of them, but I'm going to do a search for volcano and show you what one looks like. Now, these were not necessarily massive volcanic eruptions, but this one is down in Guatemala. This is Central America. Does everybody see the brown colored sort of cloud looking thing that pops through?
Yeah.
That is the volcanic eruption from a volcano called Fuego down in Guatemala, right there. And we're able to use the colors to differentiate the clouds, which are not related to the volcano, to the volcanic ash cloud, which is brown in this case. And this was actually a deadly eruption. There were some fatalities, unfortunately, associated with this eruption, yeah.
Can we look at another one to see if it's maybe a little clearer?
Yeah, let me show you one from, there's a lot more volcanoes over in the West Pacific. So we're gonna go to the Japanese satellite and find a good one here. Okay, so this is one, this is not exactly what our eyes would be able to see. It's sort of what we call a false color image. This is the Kamchatka Peninsula, which is southeastern Russia. This is the Pacific Ocean over here. Look carefully right there. See that? That is we're kind of far away that you can see the volcanic cloud going up in that respect. This looks a little bit more maybe what you would think of in terms of volcanic eruption. It's not as dramatic as the videos you see from the ground of somebody who's on the ground with a camera looking at the volcano, and it's because we're further away. But you can, this is a nice example of what volcanic eruptions look like from space. Okay, so that's all I had to share, but I'm happy to take any more weather, satellite-related questions that you guys may have. Or about meteorology, if that's something you may want to do as a career, if you have questions about that. Anybody have anything? Yeah.
What did you say the name of this website was?
Okay, so the one with all of the loops, is that the one you're asking about?
Yeah.
So do a Google search for loop of the day, and this will be the first one that comes up. Goes 16, 17 loop of the day. These are the two satellites. The most current one, it looks like this one was posted yesterday. You can click on it and it'll show you the loop that we saw. And then you can look down through all sorts of examples over about the last year and a half of cool loops that we have.
I'll post those on our Google Classroom too.
Yeah. What's your favorite loop?
My favorite loop, oh man, that's a great question. My favorite loop is one that I don't think is even on this page. But so I remember I was talking about supercell thunderstorms. These are the thunderstorms that rotate like this, and some of them produce tornadoes. The loop that I have, you're able to see the actual rotation of the cloud itself from the satellite, and that's somewhat unusual because usually the top of the cloud, the anvil cloud, is blocking our view. In this case, the wind sort of blew the anvil off to the north, and we were actually able to see the rotation of the cloud itself. Not the tornado, but the cloud rotating, which is a lot bigger. And some of these clouds actually did end up producing tornadoes. We weren't able to see the tornadoes from the satellite, but we could see the rotating clouds. And I really should have have that loop with me, but I didn't provide it. We have lots of other good ones though. Let me see, there might be another great one I can think of. Let's go back to our Himawari, which is the Japanese satellite, and look down.
I have a quick question for
Yeah.
you about that. So if the whole supercell cloud is spinning, is there a potential that we could get enough energy in that cloud that whole thing becomes like a land hurricane? That the whole thing then spins fast enough that it creates some type of, I don't know, maybe wind or just like, I don't know if it would create a funnel or not, but that could occur.
Yeah, so first of all, in terms of the terminology, hurricane and thunderstorm. So hurricanes are generally larger in scale. They're like the rotation associated with that is a lot larger than an individual thunderstorm. So you can't really call it a hurricane in that respect. There's some different things going on. But what you say in terms of the entire storm rotating and coming down to the surface, sometimes that does happen. Now the rotation of the cloud itself is not necessarily super strong. It's not enough to cause damaging wind. I mean, it'll be windy, but it's not like the tornado that would spin up in that. And so if you're in a really humid area with high humidity, high relative humidity, it is possible for these rotating storms to sort of form all the way down to the surface. The weather in that would be windy and raining, maybe some hail, but not necessarily damaging wind, I guess. Any other questions? Does anybody want to be a meteorologist? I didn't convince anybody.
I do now. There's some sweet pictures.
Maybe. Something to consider, right? Yeah. Yeah, it's a fun thing, and you're doing something that affects people's lives, especially if you're a forecaster. You're looking at a radar loop and you're saying, tornado warning for so-and-so town, take cover immediately, and you can think of that as, doing good for the world in addition to actually being your job, which is kind of neat. Yeah.
How does the sun affect like the movement of clouds like around here this morning?
Yeah, so The sun is really the driver of everything. I mean, it heats the Earth, and that is what drives all of the weather systems in general. In other words, if we could turn off the sun, of course we can, but turn it off for good, that would be the end of the weather, and it would be the end of us too. But so it's really important in sort of a large-scale perspective. In terms of a day like today, the sun is mainly just warming up our temperatures each day. You know, it's allowing us to have what we call if you go outside with a thermometer, you take the temperature every hour. It's generally going up each day and going down each night. And the sun is really the reason for that, because when the sun is up, it's heating the surface. But this type of cloud that we're getting is not really the type that would go away if the sun goes away, because it'll stick around at night. Those are more of the summertime type clouds that we saw in the eclipse. You get these cumulus clouds that are sort of being forced by the sun. So it kind of just depends on where you are and the type of cloud that it is, of whether the sun sort of directly affects it or not. Yeah.
Yes, I live in Loveland,
Mm-hmm.
and like yesterday it was really cold in the morning, but the wind was really warm.
Mm-hmm. Yeah, so there's a term for that, and we call that a Chinook wind. And what a Chinook means is if you have mountains nearby, which of course we do to our west, if the wind is blowing from west to east down the mountain, what that tends to do is as the air goes down the mountain, it tends to warm. It's called a warming wind. And so a Chinook wind is just sort of a term for strong winds coming down from a mountain. And if you remember, sometimes in the wintertime we'll have fresh snow cover, and then it'll get really windy and warm in the afternoon. And this warm wind will really quickly melt the snow. That happens sometimes around here. Those would be called Chinook winds. Now, we don't have any snow here today, unfortunately, and so we can't say that. But anytime you have westerly winds, westerly means from the west, from the mountains, coming down and warming, we call that a Chinook wind.
Does anyone else have any other questions that are burning